Okay, NSC 200 students, I am on this website that you can see here in the address bar. And when I open up this website and talk into my computer microphone, what I am seeing displayed is a representation of the sound waves that my voice is producing. Isn't that cool? You should see this when you open this particular website. If you don't see this waveform being produced, that means your computer microphone is not picking up the sound waves, and you're going to want to activate your computer microphone so that you do see this. Okay, we're going to just play with a few of the controls on the control panel over on the right-hand side. The first thing I'm going to do is mess with the oscilloscope gain, so I'm just going to change the value of 1 to the value of 2 and continue talking, and you'll notice in this case that the amplitude of the wave displayed is much larger than it was before. And now I'm going to change it to 0.5 and continue to talk, and you'll see that the amplitude of the wave displayed is much smaller than it was before. Now I'll set it back to 1.0. Now we'll go over here to the seconds per division control portion, and I'm going to change this from 1 millisecond, which is 1/1000th of a second, to 5 milliseconds. Let's see what happens. Well, in this case, you'll notice that the displayed wavelengths have a much tinier wavelength than they did before. Let's change it to 50, no, let's do 100. We'll do 100 microseconds. And in this case, you see that the wavelength of the wave displayed is much longer than it was before. I'm going to go ahead and change it back to 500 microseconds. There we go. Now what this second per division represents is the amount of time, that's right, time, that is represented between two vertical solid lines on the oscilloscope. So the distance across one square represents 500 microseconds worth of time. Now I'm going to go over here to the input control, and I'm going to click Freeze Live Input. So I'm going to make a little bit of noise while I click Freeze Live Input, and you'll notice as soon as I click this, it captured a snapshot of exactly the wave being displayed when I clicked Freeze Live Input. I'm going to turn it off so it goes back to Live Input. And now as I continue talking, I'm going to click Freeze Live Input, and there it's frozen, that brief snapshot of the wave being displayed when I click the button. I'll click it back to this now, and you can see it goes back to live input. Now over here under the input box, I'm going to change this from live input to sine wave. And now you can see a static wave is produced, and it is a sine wave that's being displayed. And I'm going to go ahead and change the seconds here to, let's go 1 millisecond. You can see that the wave got smushed a little bit. So in this case, the oscilloscope is just taking it's just taking a regular sine wave and displaying that for us. Okay, now I want to go ahead and change this to 2 milliseconds. And I want to show you, in principle, how we can measure the frequency of this particular sine wave being displayed. So we're going to have to measure 4 things to do this. So the first thing that we're going to do is we're going to measure the distance from the crest on the far left to the full crest observed on the far right. You'll notice it's 1, 2, those are 3 crests removed. And as I measure the distance from these 2 crests, I notice that's about 13.6 centimeters. So it takes 13.6 centimeters to go from this crest to this crest. We're going to call this value capital D for big distance. I want you to recognize that this distance represents 3 wavelengths because I'm measuring from crest to crest once, twice, 3 times. So it's a total of 3 wavelengths is 13.6 centimeters. Now that 3 wavelengths, we're going to make that equal to capital N. So capital N, the number of waves, is going to be equal to 3. Now we're going to measure the distance across a square, just a single square. And if I do that with my ruler, I measure that to be 2.25 centimeters. So I'm going to call the distance across one of these squares to be little d for little distance. And that's going to be related to the seconds. And then finally, we're going to measure the seconds, which is 2 milliseconds, which is equal to 0.002 seconds. So that's going to be equal to little s. Now I have all the information that I need to calculate the frequency of this wave. The frequency of the wave is going to be big N, or the number of waves, times little d, or the distance across a single square, divided by big D, which is the distance I measured, the distance I measured from one crest to the third crest remove. And we're also going to divide by seconds, the little s, which is 0.002 seconds. So if I plug all these in, 3 times 2.25 divided by 13.6 divided by 0.002, I get 248. And the units of that 248, that's inverse seconds. That's the same thing as a hertz. So I've measured the wavelength of this wave to be 248 hertz. And hey, look over here at the input wave frequency, 250 hertz. That's really close. So I know that I'm doing this method pretty well. I got really close to the appropriate answer. 250 hertz is what it should be. I measured it to be 250 hertz. And now what I'm going to do is I'm going to go back to live input. And what I'm going to do is I'm going to whistle, because I can get like a pure tone when I whistle. Watch this. Isn't that cool? You see like almost a perfect wave. Now, when I whistled, I noticed that the waves were really tight together. So I want to change my division seconds. I'm going to move that down maybe to like 500 microseconds. I'm going to whistle again, and then I'm going to freeze the live input. There we go. So I have just captured the waveform for my whistle. And now I'm going to try to measure the frequency of this particular wave. When I do this, I'm going to measure the wave from the crest that I can see on the left, the full crest I can see on the left, all the way over to the full crest that I can see on the right. And that looks to me like about 15.25 centimeters. All right, now I'm going to count the number of waves. 1, 2, 3, 4, 5, 6. So big N is going to be 6. The distance across the square, that's going to stay the same. Little d is still 2.25 centimeters. And this time, my seconds division is 500 microseconds. Oh, that might be a little bit hard to figure out. But if you use that chart that we've talked about at the beginning of the year, you'll see that this is 0.0005 seconds. So now I can do the calculation to figure out what frequency, what sound frequency I produced when I whistled. So we'll take our value of big N, which was 6. We'll multiply that by little d, which is 2.25. We'll divide that by 15.25, which was big D, the distance from, between the two peaks that I measured, the two crests. And we're going to divide that by 0.0005. Wow! I get 1,770 hertz as the pitch that I produced when I whistled. This is what I want you to do. I want you to produce some sort of sound by whistling or blowing across a 2-liter soda bottle with some water in it. And I want you to take a picture of the wave that you produced and send that to me with your calculated frequency. Isn't that cool? You can use this thing to measure sound frequencies that you produce. I look forward to seeing your results.